Group 4. Hello, Group 4. Assalamualaikum. Morning.
Morning, Doctor.
Who is the leader? Jenny Chua, Chun, Jun.
Assalamu alaikum, Doctor. Do you hear me?
Yeah. The others.
I think one of them still didn't join yet.
Uh,
First, Doctor, عظم الله أجركم.
Amin.
غفر الله لميتكم وأسكنه فسيح جناته. اللهم
Amin.
آمين يا رب.
Amin. Ya Rabbal Alamin. Mashur, call your groups
Yes.
to enter.
Yes. Oh,
Jenny, are you there? Jenny.
Yes, doctor.
Call your groups. Okay, can start. Can share slides.
okay.
15 minutes only, not more.
Uh, okay. Good afternoon, Doctor.
Yeah.
This is our group 4. We are presenting this assignment. We have the tasks A2. Then next, this is our group member. It's me, Abdullah Mashur, and Ong Kwan, and So Jing, and the group leader, Jeannie. Next, okay. Basically, Doctor, we have given this case study. There's a traction drive system. This and we want to like make the table for the table to be accurate position for the machine. And the traction drive system actually got two advantage. It's like no friction, low friction, and no backlash. So we got in this system there is a lot of disturbance. So our aim in this project to reduce this disturbance by making a controller. So next we start with the task 1. This is the task allocation, Doctor. Next. Okay, task 1. First, to start our case study, we start by the mathematical modeling. The first question we are given this block diagram and the final equation for this block diagram, and we have been asked to solve this to like mathematically show the steps how we got this equation from the block diagram.
What is the
The-
system type?
Sorry,
System type.
system is type 1.
Okay, proceed faster.
Okay, next slide. Okay, this is the procedure how we get the final equation from the block diagram by simplify. So then next question, we get we put all the values that were given to our group, and we get the final open loop transfer function. And this is the final open loop transfer function. And next question. This is the next question. We obtain the block diagram of the system using a unity feedback system. It's mean the closed loop. Yes. The closed loop transfer function. This is our closed loop transfer function. Then we do mathematically also the closed loop transfer function. Next the simulation part. To represent the open loop transfer function and the closed loop transfer function in MATLAB, we use this code. First code to represent the open loop transfer function, then the next code to represent the closed loop transfer function. Next, how to do the Simulink. And in Simulink, we use the step, and directly we put the equation inside the transfer function, and from the scope, then we can get the response. Next task 2. Task 2 is divided to 2 tasks, Doctor. Task 2A is time domain analysis, and 2B is frequency domain analysis. The learning objective of this task to learn how to use the root locus and simulation techniques to analyze and understand the stability and performance of a control system in the time domain. Next slide. First, we do the mathematically first, we analyze the system in the time domain system. So first, if we want to get the breakaway point, so we use the differential equation and the characteristic equation to get the breakaway point. Then next we obtain the K stability range of stability K by using the closed loop transfer function and the RH method. Then we obtain the range of K and the J omega crossing points. After we do the mathematical part and we obtain all the values, then next slide, we do the simulation part. This is our MATLAB code to get the root locus of the system. Basically, we use numerator and denominator. And next is the root locus. This is our root locus. As we obtain in the calculation, you know, the breakaway point is minus 13.6. It's written in the green color here. And we got also the gain is same what we got in the calculation, 26,000 plus.
What is
And
the frequency value when the system is marginal stable?
marginal stable, the
What is the frequency
frequency
value, the oscillation frequency value?
with it marginal stable,
Mhm.
it's 118, but it's not
13, okay.
okay.
118 radian per second. Continue, faster.
Next,
Uh,
the closed loop transfer function. This is same the code, but we add the closed loop transfer function. Next, by using the MATLAB, we can obtain this value. It's that the overshoot is 41%, it's so high, and our aim to reduce this overshoot actually for
Okay.
next steps. And we have the peak time and the settling time. Peak time is 0.078 and settling time 0.32. Next, the Simulink. Yes, this is the code for the Simulink time, Simulink model. Next, this is the settling time we got same with what we got for the time response. Sorry, for the MATLAB code and the Simulink, we get the same value, little bit just different. Then next, this is the comparison between MATLAB and the time domain. So we got the same values for the peak time. It's approximately a little bit different due to the steady state error, actually exactly the same in both methods. And the system is stable for, so we got from this analysis, we got the system is stable for our K that given 3,500
Okay.
because there it's between the range 0 to 26. Next, the frequency domain analysis. So here we want to use the put plot to analyze this, understand the stability of the system. Next, this is the code for the put plot.
Okay.
Then next, this is the response. This is the response, and we got the gain merging and phase merging, and next we got the KV because it's a type 1, so we need to use the KV. We draw it manually to obtain the KV, and we got the KV is 60. Then next we do the analysis manually. So we got the gain margin, the phase margin, and from the KV from the K that we have, we get the K new is 7.4 to 7.5, and we multiply the K old with the K new, 7.5 multiplied with 3,500, the old K. So we got all the same range is 26,000 plus, with a little bit different. Then the steady state error also still 0. Then from the boot plot, we got actually the KV as we show 60. So the overshoot, we got 0.017. It's a very small overshoot. Sorry, the error steady state error is 0.017, a very small steady state error. Then next the code, MATLAB code plot for the closed loop system.
Okay. Quick.
Then quick. And this is the closed loop system. We got the peak time here also. Peak gain is 5.71, and we will the frequency when the magnitude is minus 3 dB. We got 46.5. Next, we use these values to do the calculation to obtain the settling time and the peak time. So, and the overshoot also, and the damping ratio. First, we get the damping ratio. When we have the damping ratio, we get the overshoot is same what we got with the time domain analysis, 41
Okay. Faster.
and something. Next, the discussion, and lastly, we have got the peak time, settling time, damping ratio, and the overshoot. This is the difference between the time domain and the frequency domain analysis. And actually, in the frequency domain bot plot, we use the ramp input.
Okay.
So hence we got a small steady state error overall. And while we use the step input in the time domain, we got 0. And we confirm that the system stability and stability and the performance.
Okay.
The both method. Next, go to task 3. Miss Jeannie will continue. Thank you,
Yeah,
Doctor.
so for
Faster,
task
Jenny,
is the
faster.
PID controller. Yeah. For the first part is a design specification, which we want to reduce the percentage of overshoot from 41.4% to 10%. And the setting time will reduce half from 0.32 seconds to 0.16 seconds. So that the lower the setting time, the faster the system will reach the steady state and able to achieve a stable system. Plus, this one is a block diagram for the closed loop system. Yeah, with the PID. And this one is a manual calculation, so we are using the angle criteria and also trigonometry to get the value of Z. And then we will compare with the equation to get the value of KP, KI, and KB.
Okay.
This one is the MATLAB code to verify our manual calculation. So you can see the step response information, the overshoot have a 12.71% and stepping time of 0.1268 seconds is approximate to our design specification. And this one is the group locus after adding the PID controller and the step response. This one is the simulating block diagram, and we from the for the comparison between the theoretical calculation, MATLAB POP and Simulink, you can see the value of setting time for MATLAB POP is 0.1268 and Simulink is 0.166, which is approximate to the 0.16 seconds. And for the MATLAB POP overshoot, for the percentage of overshoot for MATLAB POP is 12.71 and Simulink is 14.5. It's also approximate to 10%, and our system is type 1, so it doesn't have any steady state error.
All right.
Yeah, and the discussion for output performance is that we have successfully achieved our objective since the percentage of error and setting time is reduced.
Okay.
Yeah. So in task 4, we're going to use the tuning PID controller method to achieve the best design specification. Next slide.
Name?
My name is Saw Singh.
Okay, Mr. Saw. Okay.
Yeah. So the next slide. So initially, next slide. So initially, we did our block diagram that has been constructed in Simulink. Next slide. So once we select the tune method, we will change the parameter for the PID block, and the block window will appear as shown in the figure 4.1. So the slide value are adjusted to the right to achieve the minimum setting time and overshoot. So you can see the dash line is the build before the tuning, and while the straight line is after the tuning. So next slide. So the color under the tube show the parameter after tuning, and while the color under the block show the parameter before the tuning. So the before the tuning, the overshoot is 18.7%, and the setting time is 0.141 second. And after the tuning, we'll achieve the overshoot is 0.3%, and the setting time is 0.0849 second. So the overshoot, you can see the overshoot after the tuning, the overshoot and setting time of system has been improved. So next slide. And this is a Simulink model for before and after design. Next slide. So in this Simulink model, we verify the output performance before and after design. And you can see the yellow color is before the tuning, and after the blue color is after the tuning time response. So next slide. So you can see from the response, the overshoot is approximately 0.34%, and we achieve the steady state error is 0, and the setting time is 0.085 seconds. Next slide. So this is our MATLAB code to show the performance, the time response before and after design. Next slide.
Okay. Reduced.
Okay. So this comparison of parameter between the before and after design. And as we know, the PID tuner in Simulink allow us to obtain optimal and appropriate gain value KP, KD, and KI by adjusting the slider value under response time and the transient behavior. So the tune gain as shown on the table, as well as the specification before and after tuning, and the minimum overshoot and setting time and the static error for the system is achieved after the tuning PID controller.
Okay, faster.
Next slide. Okay.
So my name is Ongwani, and now carry on to task 5. Just simply the delay controller design using the pop block. So this is an overview of the systems. This one is the delay compensator formula. So this is the overview of operations, the original system response. And our aim is to design is to achieve the percentage less than 10% and the setting time less than 0.16 seconds. So this one is a general formula of my delay controller. And since the system is already type 1, so there's no zero, there is zero steady state error, I just need to design a lead compensator. So the from per plot, so the gain margin is original gain margin is around 17.5, and the original phase margin is around 30.1 degrees, and the original peak magnitude is 5.71 and occurs at the peak frequency of 40.6 radian per second with a bandwidth frequency of 64.5 radian per second. So this is a step for me to attempt my controller design. So attempting the lead compensator magnitude at 7.336 dB. So by using the pop plot of the uncompensated systems magnitude at negative 7.336, I will get my mass frequency occurs at 64.2 radian per second. So I will use this value to find my zeros and poles. So this is the lead compensator, the formula. So after I sub into my original transfer functions, I will get these open loop transfer functions. So after the compensated, it's already gain margin of 19.3 and phase margin of 59.4 degrees. So this is the peak magnitude of 0.321 and 47.8 peak frequency, and the bandwidth frequencies occurs at 110. So this one is a simulated model for the uncompensated system and the compensated system. So this is a result obtained after the compensator. So by observing the overshoot percentage had decreased for 41.5 to 8.28, and the peak and the setting time reduced from 0.32 to 0.06. So this one showing the comparisons. So the phase mastery increased, indicating the overshoot had been reduced, and also the bandwidth and the grand crossover frequency increased to faster the transfer response. So this one is show the original state response and the compensated state response. So in clear, it's already improved the systems. So this one is the Malacop, and for numerator D for denominator, so it's original systems, and this one is the compensated systems. After I sub into, I get the pop plot and the margins of the compensated system. So by discussion, so task 2 is used to find the original system response. And task 3, we obtain the overshoot percentage has been reduced to 12.71, but it doesn't meet the design specifications, which is less than 10%, but it's much lower than the task 2, indicating a better stability. And also the setting time also decreased and meet our design specifications below 0.16 seconds. So for the task 4, it's achieved the minimum overshoots compared to other tasks, and also the setting time. In the task 5, it shows the time to reach the state response, which indicating the setting time of 0.0621, and the percentage of overshoot is relatively smaller than task 3, but it's bigger than task 4. So task 4 stand out as the fastest peak time, but in real case, task 4 may be costly. So task 5 could be another choice to implement the very fast and good stability. So for the conclusions, all tasks meet the requirements in terms of performance. The original task 2 has very significant overshoots and long setting time. So after we carry on to task 3, task 4, and task 5, we get a better system response. And task 4, since it's a tuning of PID parameters, so requires a MATLAB auto-tune tools. So this one, we will have the lowest peak time, lowest overshoot, but shortest setting time, but maybe costly if you want to implement in real case. So task 5 will be another choice, which is extremely efficient too. So this one is a reference. So that's all from our group.
All right. Thank you very much. Well prepared report, very good. So all of you may exit from the room. We ask the other group to enter.
Okay.
Thank you very much.
Thank you, Doctor.
Okay.
Hello?
Yeah. Sorry.
Okay, I share my screen.
One, two,
Doctor,
and
can you see my screen?
okay. Can she?
Wait
ISS Yemen. Who is this? ISS Yemen.
Huh?
Belfake.
Yeah, it's actually me. I used the wrong account.
Change your name. No IS, please. Okay, Cal, Wimok, and Kinteng. All right. Let's start now.
Kinteng join already?
Mm-hmm.
Okay, can. Then I
Okay.
present it now.
Start.
Okay, good. Okay, I start. Okay, so good afternoon, doctor. We are from group 2 and today we will do our group assignment presentation. This is our group members, and Ishan, Kelvin, Mok, Kinteng, and Ahmed Bafakit. And today we are going to look into the sun seeker system, and this is the system block diagram that we are going to use. Next, for our group, we are assigned with the task B1 system parameters, and this is the parameters that we are going to use. Next, I pass to Kelly Mo. Hello?
Yep. Kelvin Mok. Kelvin Mok. Dia tak ada mah.
Oh, doctor, he's jam now.
Jam ah.
Got the Wi-Fi problem.
Wi-Fi ya. Okay lah, bos. 8 lah. Sudah masuk.
So I help him to proceed with this
He
one.
just-
So in the task one,
He just arrived.
okay.
Kelvin Mok. Kelvin Mok. Sambung lah.
So, doctor, can I help him to proceed?
Tap. Okay. Go.
Hello?
Eng.
Okay, so I continue.
Yeah.
So for this one, we put in all the parameters inside the block diagram, and we get the same transfer function as shown as the question given. Next, for the part B, task 1 part B, is finding the open loop transfer function. We put in all the values of the parameters inside the KS, RS, all the function, and we get that the open loop transfer function is this one, the transfer function value. After that, we put in a closed loop, insert again the k equals to 0.5, and we'll get that the closed loop transfer function is this one, the TS. After that, we use the MATLAB to verify the
Hello.
equation that then you
So
continue.
just now I cannot. I don't know why
Okay.
for my computer audio
Continue.
there cannot
Kelvin.
mute.
Kelvin, continue.
Okay, so
Ah.
so for task Then we
Continue.
have for the closed-loop transfer function of the system by implement the gain controller k equal to 0.5 inside the system. So yeah. So and then next page. Lastly, we do the same step in MATLAB and the Simulink to verify the manual calculation answer and check for the open loop and the closed loop step response. And for the MATLAB, we implement the open loop and closed loop system by using the MATLAB function. And next. And for the Simulink model, we implement the step input block, transfer function block, and the scope to generate the step response for each system. So that's the figure of the step response. Yeah.
So for task two, we are doing the system analysis in the time domain and the frequency domain. First, we have to do the first for the manual calculation, and we get that the open loop pulse is 0 and negative 25.01. And by using the R-hash table, we get that the stability of the system is k greater than 0. And the breakaway point for the system is negative 12.51. This is the sketch graph of our system. After that, we will use the MATLAB simulation to verify our answer in the manual calculation. We get that the breakaway point is also negative 12.5 and the range of k is greater than 0. After that, we also use for the closed loop transfer function. We use the feedback function to get the closed loop step response. And we get that the system performance from using the MATLAB code, and we get the time domain, the setting time, overshoot, and the peak time.
Oh, excuse me.
So for this system,
Excuse me. And the code real parts equal to real poles. What do you mean by real?
means that not the negative part,
Nampak tak? Real parts
the positive
equal
side.
to real bracket.
Yeah, means that the real value of real and imaginary. The
Real. What do you mean by real bracket poles?
the value, the real value of the post.
The real value of the poles. Okay. Zeta omega n. Okay.
By using that, we get the system is stable. After that, we used for the Simulink to do the same approach, same function to get the system performance, and we get that the value is almost similar, and the system is also stable. After that, we will do the frequency domain analysis. In this part, we're going to find the gain margin and phase margin. So we do the block plot for the open loop and closed loop. And we get that the gain margin is positive 86.9 dB and the phase margin is 38.3 degree. So overall, we can say that the system is stable because both values are positive. And the range of stability is k in between 0 to 22,130. For the steady state error is 0.032. So this is the closed loop block plot. From here, we can get the maximum magnitude MP and the bandwidth. Bandwidth is below 3 dB from the 0, and we get that the maximum amplitude is 1.728 and the bandwidth is 50.7 radian per second. From the value that we get previously, we can get the damping ratio, settling time, and peak time, and also for the percentage overshoot we find from the graph. So this is the comparison result for the time domain analysis and frequency domain analysis. We can see that both value is almost similar, and this is what we should get from our result.
Okay.
Next.
So in task 2, we analyze the system time domain response, including the parameter like setting time, overshoot percentage, and steady state error. So from the analysis, the main performance issue identified well. If how has the long setting time, so the system will take too long to reach the steady state, and high percent overshoot, and also non-zero steady state error. So to address that issue, we propose the following design specification for the PID controller. So first is we need to reduce our setting time by at least 67%, and lower the percent overshoot to 10%, and minimize the steady state error, and also ensure the system remains stable across varying the condition. And next, so this is the closed loop block diagram that include the PID controller block. Next, in designing the PD controller, we need to find the damping ratio at 10% overshoot. By applying the formula, we can get the dominant for S equal to negative 19.5 plus J 26.64. And using the triangular calculation, we can get the Z, which is equal to negative 77.6. And next, after that, we design the PI controller to reduce the error to 0, and we choose the GPI as equal to S plus 0.01 over S. By multiplying the PI and PD controller, we can get the transfer function for PID controller and get the KD, KP, and KI. So the red color one is the transfer function of our command center system after multiplying GPIS with GS. And next, so this is the MATLAB code to get the dominant pole at 10% overshoot and to verify that our manual calculation is correct. And to verify our design, we simulate the crossroad system response in MATLAB using DES parameter. So the results show the improved performance with reduced setting time, lower overshoot, and minimize the steady-state error. Next. And in the simulating, we have used the workspace and the step info function to show all the output results. So from the figure, we can see that the signal of before and after the compensated. So from that, we can see the overshoot is reduced and the setting time is become faster, so that the system can reach steady state faster. Yeah. And next. So this is the how to we calculate the overshoot, the SS, and so on. So and before the compensated, so our overshoot percentage is reduced from 30.92 to 12.77. And for the setting time is from 0.31 seconds to 0.15 seconds. Yeah, so that's from the result, we can conclude that our system implemented with PID controller is met all the desired specification.
Quick.
Kintang.
Kintang. Sleeping. Oh. Kintang. Kintang sleeping, ma?
Oh, he also got Wi-Fi problem.
Okay. Eng, sambung.
Okay. So for the task 4 is for the tuning of the PID parameters. We are trying to adjust the graph so that we can achieve the minimum setting time and overshoot of the system. So we can see from this one, the tune response is the solid line. Okay, continue.
Yeah, the story, the Wi-Fi disconnecting every 2 minutes. So next. So here we can see the gain parameter and the performance from the PID tuner. So we can see after tuning the left one, the rise time, setting time, overshoot is almost approximately 0, and the new gain parameter is shown above. Next. And then we apply the tune parameters to the new simulating model. The above one is the before tuning and the below one is after tuning to compare the result. And then we can see the new comparing the before and after tuning. The blue color one is after tuning. We can see that the output response is almost like the input square wave with minimum overshoot and setting time. And then we use the cursor on the oscilloscope to measure the overshoot percentage, steady state error, and also setting time. And then to verify our result, we use the MATLAB code to obtain a more precise value. And we can see that the setting time overshoot is improved significantly. Here is the table that compare the three of the performance we want to obtain, and we can see it's almost 0, and the new proportional gain, derivative gain, and integral gain is also shown here. So we can conclude that the PID tuning of PID tuner can let us obtain the best possible specification.
Okay, faster.
Okay, for task 5, we need to design the controller using
lead lag using lead lag from the bot plot. Actually, first we need to visualize the desired values from task 3, which is 0 for setting error, 10% overshoot, and 0.205 for setting time. Here is the value at the you can see actually the block diagram at the bottom. And next slide, we can see actually as we achieve the value from phase margin and gain margin from task 2, you can move actually next. And next one is actually the closed loop transfer function. We have the gain at the maximum frequency, which is 3.68, and maximum frequency is 31.10. Next. And for the compensator design, we have the set error for 0.023. And for overshoot, the original value was 31, and for set time was 0.3. For the desired value, as we mentioned earlier, we can actually find the damage ratio for the 10% overshoot, which is 0.591. And from the damage ratio, you can find the new phase margin, which is 58.58. For the set errors, the set errors are actually very close to 0, so there is no need to design a lag compensator. Next. For the compensator design, we have the phase max, which is equals to the new phase margin minus the old phase margin plus the correctness factor, which was 10. And then we can find the value for beta, which is 0.33. And from the value from beta, we can find the gain max, which is 4.81 dB. Next. From the maximum gain, we can find the maximum frequency, which is 22 rad per second. Next, we can find the value for the 0, which is the maximum frequency multiplied by the square root of beta, which gives us 12.64. And for the ball, we need to divide the value for 0 by the value of beta, which is 38.3. For the gain, it is 1 over beta, 3.03. And here's the value for the lead compensator. Next, we can see the equation. Since we will not design a lag compensator, here's the equation. Next, here's the transfer function, the bot plot for the open loop compensator system, and the closed loop. We can see the maximum gain, which is 2.01, and the bandwidth, which is 74.56. Next. From the obtained value, the parameters for the new compensator system is 46.8 degrees for phase margin, 54.4 for the gain crossover, and 74.56. From the values of the compensator, you can say that the system has system's stability has actually increased, and you can actually summarize that the system overall is better than the uncompensated system. Next. Here's the block diagram for the Simulink. Next. And here's the simulation result using MATLAB. We got 0.31 for the old uncompensated system for certain time, and the new value is 0.141. Okay. And the overshoot is actually 16.9.
All right.
Next.
Good.
For the time peak, we got actually 0.06. And for the steady-state error, we got 2.3, the power of 10 minus 5. Given this result, we can say that compensated system has less overshoot than the older one, and can say that the system has actually improved. And we can also, from the value of the steady-state error, say that there is no need to incorporate a lag compensator.
Yeah.
Next. From the tasks, we can say actually a gradual decrease in the values for the peak time and static time and overshoot, which actually means better systems. For task 5, we actually have a higher value for overshoot, but overall it's better than the task 2. For task 4, actually we have a lower value of peak time and static time, which means that the system can achieve the stability faster with less fluctuations. Also for the overshoot, it has 0.60, which actually also means better stability overall. And next page, you can see the discussion more thoroughly. Next, I will leave the part for the conclusion.
Okay.
So in this assignment, we design an analysis and analyze the science cycle system by using our knowledge in control system design and also using software such as MATLAB and Simulink. We first by doing a mathematical model of the system, and then we analyze the system in both time domain and frequency domain. And then the designing part begin by we design a PID controller to improve the performance of the system. We also tune the PID controller to get an even better result. Besides using PID controller, we also design a lead compensator to as an alternative way to improve the performance of the system. And comparing the result, we can see that our assignment was a success, and we also conclude that the control system design is very important in engineering application. That's
Thank you.
all from our group. Thank you.
Okay, Shashani, group 2 can exit. Okay.
Doctor, can we submit our latest slide? Because we have to do some modification in the reference.
You send by email. Email
Okay,
to
so also send in two format, right? The PDF
Uh,
and PPT.
yeah. Send email to me.
Okay, thank you, doctor.
Okay, thank you, Doctor.
Thank you, Doctor.
Okay, group 11.
All right, Doctor.
11. On video, please. Group 11 on video.
Doctor, you can hear me, right?
Yeah. Another 2 members. Group 2 on video. Sorry, group 11. Miss Tang, Lau, Ko, and Amro. Miss Tang, where is your other 2 groups? 2 members lost.
They're coming in.
Amro, on your video. Okay, can proceed. You already 10 minutes overshoot. Miss Tang, can start. Okay, can start.
Oh, sorry, Doctor, I was muted. Can you see the slides right now?
Yes, yes. Slide number 1, please.
Okay, good afternoon, Doctor. This is Group 11 assignment. So these are the members of the team. Here's the content for the presentation today. And this is the diagram of the Sunseeker system. And here's the block diagram, which include all the gain and the feedback and everything.
I'm sorry, Doctor.
Yeah.
Can you admit Junsen?
Yes, already.
Okay, thank you.
Continue.
Okay, this is the system parameters, every parameters for the B4 set. And the system explain, actually it's about controlling the alignment of the star of the space vehicle. So we align it to the sun, and we have like something like sensors that detect the error signal and return it back as a feedback. Then we just try to align this align the space vehicle to the system. Here is the objective of our assignment. We start first with the task 1, which is the mathematical modeling. First thing, which is the open loop transfer function. Since we have like 6 gain, which are like we can see the G1 until G6, we just multiply them together, we get the gain, and then we can do some simplification since we have b is equal to 0. Then we can substitute the parameters that's given in the table to get the open loop transfer function. Then we can consider this unity feedback, and we can use the formula transfer function is equal to g over 1 plus gh, and we will consider the h is equal to 1. So we do the calculations and the fraction, and we get the new new closed loop transfer function. Then we will try to plot this open loop and closed loop in the MATLAB. So we just do the numerator and denominator. We get the transfer function. then we display. Then the same thing with the closed loop. We just put the coefficients of the like the in the numerator and denominator, and then we do the subplot, and we get this result. This is the open loop, and the downside one is the closed loop output response. And for the system analysis, frequency domain will be represented by Ms. Tank.
For task 2, we analyze the sun-seeker system in both time domain and frequency domain. The importance of this task is to understand the system stability and also performance. So we determine it using two methods, which is calculation methods and MATLAB methods. After we perform both methods, the outcome are showing identical results. For part C, we analyze the system in time domain in order to get the system performance. After we analyze using MATLAB coding and Simulink, we can clearly see that their performance and their outcome are almost identical and showing a stable system. For frequency domain analysis, in this task, workflow analysis is performed for both open loop and closed loop system. At first, we perform open loop workflow analysis. The value of gain margin and phase margin is obtained from the workflow at each shot, and both are showing a positive value. This indicates that the system is stable. To find the range of stability gain, we can use 20 log k equals to 69.9 dB, and we calculate the k value.
Actually, you're on which slide? Because maybe I'm...
Erdin. Next. 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 Sorry. Next. Since the system is type 1, as it has pole at origin, we can calculate the steady-state error using the formula shown in the slide. After that, we perform workload analysis for closed-loop system. We can determine the maximum peak value and the bandwidth. Then we can use the value to determine other system parameters such as settling time, damping ratio, percentage of overshoot.
Questions? Command syntax feedback bracket k multiply g comma 1. What does it mean?
Sorry, which one?
T equal to feedback bracket k multiply g comma 1. What does it mean?
It is a closed loop. It feedback the result to the input.
Correct. Lau, correct. Lau Shihong?
Yes.
Correct. Feedback bracket kg.
Actually, yes, because k multiplied with g is the gain is insert to the system g, and the one behind the comma, it means that it is the unity feedback to the system.
Oh, okay. Close loop lah. Okay. Continue.
I'm going next. So from the table, we can clearly see that the overall system parameters are almost identical. This indicating a consistent transient response characteristic between both analyses. However, there is a discrepancy in some parameters, likely due to different methods or approximation in each analysis. The system showing a stable characteristic in both analysis. Thank you.
Continue, Pastor.
All right, so for the PID controller, we need to see the parameters so we know what thing to improve. So since we have the overshoot is very high, then I decided to make it like 20% to reduce it and do some changes also with the settling time and the steady state error. So here, after we decided it be 20%, so we get the zeta value. From the zeta, we can get the theta value using cosine inverse. And here we draw the zeta line to get the intersection with the root locus, so we can get the dominant pool. And basically, this dominant pool will just give us the old TS. But since we need the new TS will be 0.1, so we just since we have like the theta, and also we can get the real part using the formula TS is equal to 4 over real, so we can get the new real, which is 40. Since we have now the adjacent and the theta, we can get the opposite. Then from the opposite and adjacent, we can know the new dominant pole. Then we need to get the ZC, so we can use the angle criteria to get the theta C first. Then after we get the theta, we already know the opposite, which is the imaginary part, but we don't know the adjacent, which is the distance. So we can calculate this distance using Pythagoras, and when we get this distance, we just minus. So minus 40 minus 97, we get this value minus 137.48. After that, we can construct our GPD, and we can suggest GPI 0.01, any value that's close to 0. Then we get the GPID, which is we just multiply them together. Then we will multiply it with the open loop transfer function. And then we can get the gain K using the magnitude criteria by substituting the S with the dominant pole. Then we can compare this one with the standard formula, so we can get the Kp and the Ki. After we get the Kp and the Ki, we just put these values in the block diagram of the PID. We construct this PID with the open loop and this unity feedback and everything. And we try to get the system response. And as you can see here, the overshoot has been reduced. It's like below 20%. And here also the system, the settling time reduced. So we have this in summary. We can compare the compensated and uncompensated system, and from the values we can see that we improved our transient response and also the steady state, which means the transient and the steady state response. So after that we have the tuning method, which will be represented with my member.
Thank you, Amro. I'm Chunson, and I'll proceed with the task 4, which is the tuning method. There are two types of tuning method being used. Firstly is using Ziegler-Nichols method and also using auto-tuning. So let's see about the Ziegler-Nichols method. From task 3, we obtain that the value is of the K, three types of K, which Kp is about 0.133, Kd with 9.72 10 about -4, and also Ki with 1.33 10 about -3 is shown as a figure 4.1. And then by using the formula of GPID, and then we plug in inside our MATLAB, we obtain the closed loop function as shown as figure 4.3 inside the MATLAB. Okay, next. Here is by using the Ziegler-Nichols method, by running the MATLAB codes. And actually there are two types of things need to highlight, which is using the GPID as a variable, which we declare with our gain for the PID with the function. And then we obtain it by using G multiplied by GPID, we get about the open loop. To get about the closed loop, we're using OL over 1 plus OL, and then we need to call out with the plot curve, so that we're using step function with closed loop, and then we obtain the result of figure 4.4 with time response by Zinger-Nichols method. From this plot, we can obtain two particular information, which at the time peak is about 0.103 with the amplitude of 1.18, which is the overall tuning gain from the Zinger-Nichols method. Next is using the tuning of auto tuning of PID controller. So by replacing with the PID block, we can using the function of auto tuning by referring with figure 4.6, and that's a tune button at the below, so that we can adjust it with using tuning method. Next, is the first trial of using the tuning. We gain a result that not actually optimized. It's actually get about like a little bit overshoot, so that the result is about 5.48%, which is not the optimized expected result we get. So we try another try by using pull it to the right maximum. Next slide. Here is the maximum tuning result we get. It's about like nearly close to 1. So you can see that the percentage overshoot is about 0%, and the rise time is about 0.0051 with a setting time of 0.00997. It's very quite precise result we get. So we can do a summary that we need to get about this tuning. We need to plug in with the control parameter, which is P with 1.1197, I with 3.4178, and also D with 0.055234, so that we can obtain this result. Next, here is the output response after we put inside our PID controller and we run again. We get a two result. One is the complete to the 1, and also we can see from the data beside with a value of 1.001 is the peer closely near to 1 is just with the difference of 0.1, so that we can determine that it's a very good result from our output response. Next, here's the summary of the tuning result. From the task tree below, we can obtain that the uncompensated result is of overshooting is 67.9%. After being compensated, we get about 10.3%. But we need to improve it by using two types of tuning, which is PID auto tuning and also Zinger-Nichols tuning. By comparing these two, we can see that PID auto tuning get us a very best result with 0% of overshoot, but Zinger-Nichols result nearly close to 0, but it still have 0.18% of the overshoot result, so that we can summarize that auto tuning actually brings the best tuning method for us. So next, I would like to pass this session to my groupmate Xu Hong.
Okay, thank you, Sun. So for this part, we have to use the desired value that we taken from task 3A, and this insert in this table. And for part B, this is the schematic diagram that I draw for the system that insert the lead-led controller block. Okay, next. Okay, for this part, we have to design the lead-led compensator. So we have to determine the bandwidth first by the formula. The bandwidth is equal to 4 over settling time times the damping ratio, and the next. Okay, then oh no, the slide before. And we can get the bandwidth is equal to 115 radians, and we have to choose the new omega is equal to 0.8. This is nearly equal to the bandwidth radian, and which is 92.6271 radians per second. And the hybrid frequency is equal to 0.1 of the new radian. It is because we have to take it 1 decade below the new radian, which is equal to 9.26271. And the desired phase margin is equal to 48 degrees. Is it taken from this open loop phase margin, in the figure 5.2. All right, and then we have to design the transfer function of the lead-led compensator where the zero of and pulse of the LED compensator is 9.267 and 0.1398 respectively, and the zeros and pulse for the lead compensator is 21.8 and 155 radian respectively. Okay, next. All right, this is the open loop dot plot that we get from the MATLAB, and we can find that the phase margin of the system is 58.3. It is slightly different from our desired value. Okay, next. And this is the closed loop plot for our compensator system. And we can find that the bandwidth is equal to 198 radian. This is different with our desired value also. And from our view, it is because of the effect of the lead compensator and the lag compensator will affect each other so that the value will be changed from our desired value. Okay, next. Okay, this is the investigation of our design, and it is mentioned before, like the phase margin of the system is 59.8 degrees, is slightly different with our desired value, and there's a difference of 11.8 degrees, and the bandwidth is 198, and actually the desired value should be 115, and the reason is mentioned also just now, and it is the effect of the combination of lilac compensator. Okay, next. And here is the schematic diagram that I put in the Simulink, where the result is also coming out like the steady state error of the system is 0 after I simulate this system in the MATLAB. And the output of the system will be come out to the MATLAB in the MPOW, and it is corresponding to the timeline. Okay, we can see at the next slide. This is the graph that I get from the Simulink. Like the output is insert to the scope, and we can find that the steady state error is 0 as the output is equal to the input. And we have to notice that the input is get into the system at t equal to 1. Okay, next. And here is the result that I get from the MATLAB when I use the command step info out.system.data and out.system.time. And here's the data that we would like to get from the system just now. As the transient time is 1.11. Actually, it's not 1.11. Should be 0.11. As because the signal is get into the system at t equal to 1, so we have to minus 1 if we would like to get the data that relating to the time. So actually the actual result, the data that we would like to get is in the figure at the right, as the settling time is equal to 0.112 seconds. Overshoot is 20.479%, and peak time is 0.02, and the steady state error is equal to 0. Okay, next. So it is the comparison between the desired value and actual value. Actually, we can say that it is slightly the same. Okay, and we can conclude that our designation is our design is achieve the desired value.
Okay, conclude.
Okay, conclude. Next. Okay, this one is the comparison between each task. So we can say that the best design that have the best performance is in the task 4 because the overshoot is 0%, and the settling time is the fastest because it is equal to 0.01 second, which is the shortest one, and the steady state error is 0. Okay, next. Okay, the conclusion is in all the tasks we have achieved the objective that we mentioned in the beginning of the presentation. All right, so that's way to analyze the conclusion. Okay, next. And here is the
Okay,
difference that we get from the our project lah.
all right, thank you very much.
All right, thank you, doctor.
Shani, thank you. Jazakallah khairan.
Yeah,
Shani.
doctor.
Miss Tang, thank you.
All right, doctor. Thank you.
Group. Now is group 10. Group 10, eh?
Yes, doctor.
Yes.
Group 10?
Yes.
Okay. Share slide, please. Present.
Okay. Good afternoon, doctor. We have group 10, and now I am going to present about task 1. So for the part A, I use block reduction method to prove the transfer function, and I get the same as the question shown. Then after that, I sub the value into the transfer function, and I get the transfer function is equal to show at the slide. Then I add again to get to the system and calculate the closed loop transfer function. Next, I use the MATLAB code to determine the open loop function and the closed loop function. Then from the MATLAB result, I get the same as my calculation. Then for task 2, from calculation, I get the breakaway point is equal to -5.2. Then the stability of gain range is equal to 0, less than k, then less than 46.37 times 10 to the power of 3. Then I get the j omega crossing point is equal to plus minus j 82.77. Then next, I use the MATLAB code to determine the stability of range stability of the range of the gain k, then the breakaway point and the j omega crossing point. Then from the group locus, I get the almost same result with my calculation. Then yes.
What is the frequency of oscillation when the system is critical stable?
Critical frequency is nearly 82.1 radian per second.
Okay, proceed faster.
Then next is to find the peak time, setting time, overshooting, and steady state error. I use the MATLAB code to get the closed loop transfer function, and here is the result that I get from the graph.
Fong.
Yes.
What do you mean by function? ABS?
ABS is get absolute value from the graph.
Positive.
Yeah. Modulus.
Okay, all right. Faster.
Then next, this is the simulating module, and next from the From the simulating module, I get the almost same overshooting, percentage of overshooting, then setting time, peak time, and the steady state error with the MATLAB code. Then next, for the buck plot, for frequency domain, then I get the positive value for gain margin and the phase margin. Then it shows that the system is stable. Then next, then I draw the negative 20 dB slope to get the KV and calculate the steady state error, which is 0.0125, and from the gain margin, I calculate the stability of range is equal to 0 less than K less than 10.35. Then next, then from I use the closed loop transfer function to get the frequency this plot diagram, and I get the maximum magnitude is equal to 8.98 dB and the bandwidth is 39.4 radian per second. Then next, then I use the code to determine the damping ratio, peak time, setting time, and the percentage of overshoot, which is shown in the slide. Then next.
Hong,
Yes.
what do you mean by squeeze? Previous slide, please. Squeeze magnitude. What do you mean by squeeze magnitude?
Line
number 4, 20 log 10 squeeze MAG.
Is
don't know. Okay,
not
continue.
sure.
Continue.
Then then I compare the time domain and frequency domain. Then it shows that both system is stable, but the range of stability gain and state error are not same. So I think they are not identical. Then next is task 3, which is my teammate part.
Okay, good afternoon, Doctor. So actually part 3A, we have the design specification. So based on the outputs of the response performance from task 2, we established the design specification to improve the system performance. So we have the steady state error, it will be from 0.054 to 0. And the overshoot percentage, we will reduce it from 55.93 to 20%. And the settling time from 0.7755 to 0.1939. And so part B, we will draw the closed loop block diagram. So we start with the reference input, which is the step input. And then we will connect it to the error signal, which is fed into the PID controller, consisting of proportional, which is the KP, and the integral, which is KI, and the derivative, which is KD. And then the output of the PID controller is then passed to the plant with the GS, which is the actual equation. And then the feedback loop is completed by feeding the output back to the sensor to compare the reference input. Okay, so next, so task 3C. Okay, so now we will get to know the damping ratio and yeah, the damping ratio from the graph, and also what's the name? The domain, what?
Mean the dominant pole?
Yeah, the dominant pole. Yeah, dominant pole. Okay, so next, please. Okay, so now we will have the TS. We'll find the TS new. So we can get the omega n. And after the omega n, we can get the closed loop poles by the equation. And after that, we will get the yes, doctor.
Continue faster.
Okay. So now we will get the angles of every single part. Okay, of every single part. Okay, now. And then we'll get every KD and the KP new and the KI new for the new specifications. Okay. And now that is the coding of task 3C. Okay. And that is the output of the graphs of the new inputs that we will get. Yes. This is the bot plot. Okay, so that is the Simulink block diagram that we made from task 3B actually. And that is the output, which is actually quite similar, but there is some differences between the actual specifications that we did, which is shown in part 3E. Yeah. So there is some error percentage that occurred, but yeah, it's quite similar.
So for task 4, we use the Simulink model that we have developed in task 3 and with the parameters calculated in task 3. So this is the plot obtained before tuning and after tuning process. So by looking at the system parameters, we can see that the both gain margin and phase margin for block and tune results are positive. And also the gain crossover frequency is larger than the phase crossover frequency. Hence the system is stable for both before and after tuning process. Besides, it also shows that the percentage of overshoot has been decreased from 27.3% to 12.4%. So it should, however, the rise time and setting time are increased compared to the before tuning process. So we can conclude that the overall transition time is increased, although the low percentage of overshoot is obtained, which means that it is still not an optimal result. Because of this, so we adjust the slider values for response times and transition behavior. After this, it shows that the percentage of overshoot is also decreased. Meanwhile, both the rise time and setting time for this time can be decreased respectively. So it indicates that optimal results can be obtained with shorter transition time and low percentage of overshoot by adjusting the slider values. So,
Doctor. So now I continue with task 5. Task 5, basically task 5 is to design and lead-lag compensator. So our design specification is same as the task 3, which the overshoot percentage should be reduced to 20%. Certain time will be quarter of the original, and also the stat error should be 0. Okay, next. So this is the closed loop block diagram of the lead-lag compensator system. Okay, first of all, you need to set the KV. Since this is the type 1 system, so the KV should be set to 250 so that we can get the steady state error approximate to 0, which is 1 over 200
250, we'll get 0.004. After that, we use the initial value theorem to find the maximum K so that we can achieve the KV equal to 250. Then we use the spec design where the TS is equal to 0.1939 and zeta is 0.456 to find the omega bandwidth. Okay, so we continue. We need to select a new phase margin, omega of the new phase margin, which near to the omega bandwidth. We multiply 0.8 into the omega bandwidth and we get 47.77 radian per second. At the 47.77 radian per second, we can get the phase margin, the phase is negative 172, which means the phase margin is equal to 8 degrees. So follow our spec design, the overshoot is 20%. So the phase margin required phase margin is equal to 48.1 degree. By adding the 5 degree correction factor, the total required phase margin should be 53.1. Hence, the lead compensator must contribute a maximum phase margin of 45.1 degree. By using the maximum phase margin, the maximum phase, we use the formula inverse of psi 1 minus beta over 1 plus beta. We can get the beta equal to 0.1708. Now we design our lag compensator. The zero of the lag compensator should be 1 decade below the new phase margin, the omega new phase margin is 4.777, and the pole of the lag compensator is equal to beta 0 of the lag compensator, which equal to 0.8159. Hence, we will get the system of the lag compensator. Then the lead compensator, we obtain the 0 of the lead compensator by using the formula omega phase margin. The new omega phase margin times with the square root of the beta, you get 90.74. And the pole of the lead compensator will be 0 of the lead compensator divided by the beta, you get 115.6. And finally, we multiply all the lag compensator, lead compensator, and the original function, original transfer function, you get the final lead lag compensator system transfer function. By using the MATLAB, you can get the plot of the open loop system. So we can see the phase margin and also the gain margins are positive value, which means it's a stable system. However, you can see the phase margin from the plot cost is equal to 51.808 degree. It is close to our desired phase margin 48.1. Then we analyze the property of the closed loop compensator system so that we can find the peak gain, peak frequency, and also a bandwidth from the plot. Okay, next. So lastly, we need to simulate the compensator system in the Simulink. Next. After we simulate, we find our overshoot percentage is 24.5% and the peak time is 0.12 seconds. Next. The settling time is 0.2445 and also is similar with the open loop the compensator system by using the MATLAB system step info of the closed loop function. Next. So here is the comparison of our design spec and the output performance. Although the output performance is not exactly same as the design spec, but the lead compensator is successfully reduced the overshoot to 24.5% and the settling time to 0.2445 with the zero steady state error.
So in task 6, we are comparing the approaches that been used in task 2 to task 5. So we are able to obtain all the stability and response characteristics. However, we are able to determine which approach is the best and effective since it depends on the type of performance that we want for the system to have. So for example, if we run a system with robust stability and performance, then the approaches that be used in task 5, which is link-like control design with block plot, will be better since it provides comprehensive insight into how the system respond to different frequency in order to improve the stability and provenance. If we take another example, like if we want to have a system with quick and simple performance, then tuning a PID controller method, which can be used in task 4, will be always effective due to their simplicity and widespread applicability. So that's all.
Okay.
So you can see the compare. Yeah. So in conclusion, that the assignment was able to be accomplished and we are able to achieve all the objectives. Yeah, that's all.
Thank you very much. So Group Joanne can exit. Thank you very much.
Thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Group 13.
Hi, Doctor.
Martin. On video.
Wait for a moment. Yeah.
Call your groups. Okay, start.
Start. Afternoon, Professor. So we are from Group 13. So this is our group member, Yongxiang, Chicha, Martin, me, and Rama Hussein. So the aim of this assignment is to analyze and design the control system for the traction drive system as shown in Figure 1. And the parameter used is the set A5 as shown in Table 1. So for the Figure 2 is the system block diagram for the track systems. So the assignment also involved that theoretical modeling of the systems, time frequency domains analysis, design the KIP, tuning, and the link-like controllers. This is the objective that I mentioned just now.
For task 1A is by we reduce the block diagram by using the block reduction method, which combine the block in the middle and the side. We can reduce it into the closed-loop transfer function, which is RKM over S times LMS plus RM times JTS plus BM plus KB KM. And for task 1B, by using the set A value, set A5, we simply just plug in the value and we calculate it. Simplify it, we can get the open loop transfer function as 0.0266 over 0.004 S cubed plus 0.2749 S squared plus 2.1108 S. As for the closed loop transfer function with unity gain, we simply put a K gain value and we can calculate the value by using the equation closed loop transfer function equal to KGS over 1 plus KGS, which the value we'll get is 133 over 0.004 S cubed plus 0.2749 S squared plus 2.1108 S plus 133. And for the task 1D, for the MATLAB code, we simply just define the numerator and denominator and use the transfer function method TF, numerator and denominator. We'll get the exact result from the calculation. As for closed-loop transfer function, we can use the feedback, which is G times with gain K and feedback unity of 1, which is same as the result from calculation. As for Simulink representation, we use the transfer function block, TF block, and the gain block, which is the triangle. for 5,000 gain and a unity path back with a summing junction. And that's the result for the open loop transfer function and the closed loop transfer function in Simulink. Now I will pass my time to Rahmat for task 2.
Assalamu alaikum warahmatullahi wabarakatuh. Now I'm going to explain my part, which is task 2. First, I replaced the given parameters into the transfer function given to calculate the range of stability gain. Next. Next slide. And this is the transfer function of the this is the transfer function, and then I got the open loop transfer function, which is the transfer function multiplied by the gain. Next. Now I'm going to calculate the range of stability gain using the closed loop transfer function, which is equal to the transfer function multiplied by the gain divided by 1 plus the transfer function multiplied by the gain. And then I used the Routh table to get the range of stability gain. Next. So I equated the I got the A, which is the A and the B and C. So I equated the A equals to 0, and then the C equals to 0. So from equating the A equals to 0, we got K less than or equal to 56,925.26, and then for C is equal to 0, we got K greater than or equal to 0. So the final answer for the range of stability gain is K between greater than or equal to 0 and less than or equal to 56,925.26. Next. And this is the root locus sketch. First, we have the poles, which is 0, negative 7.76, and negative 702.84. Negative 7.76 and 0 collide and create an arc to infinity. So we have a breakaway point, which is negative 3.87, and the JW crossing on the positive and negative side, which is J234.6. Next. And then the calculation of the breakaway and JW crossing points. First, the breakaway point, I calculated I got the breakaway point using the differentiation of GS and HS equals to 0. So finally, I got the breakaway point negative 3.87 because it is between 0 and negative 7.74. Next. And then finally, in the calculation part, I got the JW crossing by getting the characteristic equation, and then I used the Routh table and used a row of zeros to get the JW crossing, which finally I got 234.6 G. Plus or minus, plus, okay. And next. And now into the MATLAB results. So this is the root locus, which is very similar to the root locus that I draw by hand. Next. This is a zoomed in photo of the root locus so that I can compare the MATLAB results with the calculation results. So first of all, the poles are 0 and negative 7.63, which is very similar to my calculation. And then The breakaway point is negative 3.84, and the JW crossing is 234.27. Next. And then the step response of the closed loop transfer function, which shows that the system is underdamped. Next. And then this is the Simulink results of the open loop transfer function. The orange line is the input and the blue line is the output. Next. And then this is the Simulink results of the closed loop transfer function. As you can see, the output, which is the blue line, is very similar to the step response of the MATLAB code. So, which means that the Simulink, shows that we got the correct answer. Next. And then this is the dot plot of the open loop transfer function. We have the magnitude dot plot and the phase dot plot. First, we got the gain margin equals to 21 decibels, and the phase margin is 18.2 degrees. Next. So the gain margin is 21 decibels and phase margin is 18 degrees. And gain crossover frequency is 73.86 radians. And phase crossover frequency is 21.44 radians per second. Next. And then this is the dot plot of the closed loop transfer function, which shows that the gain margin is 20.2 decibels and the phase margin is 23.6 degree, with a phase crossover frequency 73.9 radians per second and gain crossover frequency 30.5 radians per second. Next. And this is the overall results. We have the peak time, settling time, and percent overshoot of the step response that we got using the MATLAB code. So peak time is equal to 0.14 seconds and settling time is 1.05 seconds, and percent overshoot is 60% with a steady state error of 0. And finally, the system is stable. Next. So I'm going to explain the code. So first I inserted all of the parameters values, and then next. And then I got the transfer function, and then the transfer function is going to be displayed on the command window, and then the root locus is going to be plotted using the transfer function that is calculated above. And then we're getting the open loop transfer function, which is the transfer function multiplied by the gain, which is given equals to 5,000. Next. And then the open loop transfer function is going to be displayed, and the dot plot is of the open loop transfer function and then we're gonna get the dot plot of the open loop transfer function, while also showing the gain margin, phase margin, omega GM and omega PM in the command window. Next. And then margin open loop transfer function means that it's going to show the gain margin, phase margin with the gain crossover frequency and phase crossover frequency at the top of the dot plot. And then we're getting the closed loop transfer function using a feedback function with a unity feedback. And then we're going to display the closed loop transfer function on the command window. And then we're going to get the plot of the closed loop transfer function. Next. And we did the same thing, the same calculations and we used the same functions as we did in the open loop transfer function for the bot plot. Next. And then we got the step response of the closed loop transfer function, and we got the step info to be to get the settling time, percent overshoot, and peak time to be showed on the command window. Next.
Faster, Rahma, faster.
Okay, and then finally we have the stability analysis function. So if all real poles is less than 0, display the system is stable, and else if the system is unstable. That's it. Thank you. This is the explanation and summary of my task.
Next.
Okay, let's move to the task 3. We is designing the PID controller. So our subject's design specification will be the steady state area will be 0, and then we hope our overshoot will be 20%, and then the setting time will be 4/4, which is the original setting time divided by 4. So we hope our setting time will be 0.2617. So below is our closed loop block diagram, which include the PID controller. Next. So first, for the rule of course, we find our CL pose first. So since our overshoot is 20%, so we point to the overshoot, then we find the CL pose. Then we calculate the settling time, which is 4/3/3. Then we got our settling time, which is 1.04444. Then we divide the setting time by 4, we get 0.2611. Then from the new settling time, we get the omega n. Then our omega n will be 0.833.6 radian per second. Then from that, we can calculate our desired CL pose, which is negative theta times omega n. Then we get our value negative 15.32. Then for the imaginary CL pose will be J omega D. The omega D will be omega n square root 1 negative theta square. So we get our imaginary CL pose will be J 29.9. Next. So we can draw the triangle graph, then we can calculate the angle of our 0, which the ZC, theta C. And then we get our theta 1. Theta 1 will be the 117.13, and then the theta 2 will be 104.24 degree, and the theta 3 will be 2.511. So since the theta 1 through 3 are the poles and the theta C is the 0, so our formula will be theta 1 plus theta 2 plus theta 3 minus theta C equal to 180. So we get our theta C is 43.88 degree. Okay, after getting the degree, we can calculate the distance between the CL poles and our ZC. So the difference between two positions will be x. The x will be 31.09. After that, we can calculate our position of our ZC will be negative 31.09 minus 15.32. So JC will be negative 46.4. So hence we can get our PD controller with K square root with K blanket S plus 46.4. Next. So for our PI controller will be K over blanket S plus 0.01 over S. After that, we can get our PID controller. We multiply our PID controller to our transverse functions in order to calculate the K. So we let the K equal to post over 0 and then substitute the S with the CL post, which is the 15.32 plus J 29.9. So we get our K equal to 240.35. Next. Then we let our PID controller compare with the formula that KD blanket S squared plus KP over KD S plus KI over KD over S. So we get our KD equal to 240.35, and then we get KP equal to 111.57 and KI equal to 111.54. Then we enter the value of KP, KD, KI equal to PID controller. So the P is the proportional is the KP, the integrate is the KI, and the derivative is the KD. Next. Hence, we test our circuit in the Simulink, and from the display plot, you can notice that the steady state error is very low, with negative 6.49 times 10 power negative 5. So it's approximately to 0. Next. So we can also get our overshoot from our we can get our overshoot from the output graph. So we can notice that the peak value is 1.275 and the final value is 1. So 1.275 negative 1 by divided by 1, we get our overshoot is 27.5%, and our steady state error is 0. Next. Then for our settling time, when our value when the value is equal to 0.98, we got our settling time is 0.231. Next. And we can get our value from the command window as well via the to workplace block in the Simulink. So we just use the state infos in the command window, then we get our setting time is 0.2307. The value here the setting time value here we have to minus by 1 because for the Simulink, right, the output graph of our system is start from 1, no start from 0. So all the value at the time, the transient time, settling time, the bit time had to minus by 1. Next. So here we go. So the output performance, the steady state error we got is 0. Yes, we adjust the same with what we want. And then the overshoot we got 27.5%, with a bit higher than what we want, and the setting time is 0.2307, which is very close to our design specification. So it can be concluded that we have partially achieved our design specifications. Yeah. Next. Okay.
So for the task 4, which is tuning the PID controller, so as use back the KP, KI, and KD from the task 3, it is found that after tuning, we found that the percentage overshoots is decreased to 10.6% and the settling time is 0.96 seconds. This is the results. MATLAB systems thinks that this is the best specifications for the control systems. But the overshoots is increased, but only the settling times is longer compared to task 3. So in order to improve the settling times, we adjust the response time and the behavior in the control panel of the PID, and the results shows that compared to before and after, the percentage overshoot is decreased around from 10.6% to 9.89%, and the settling is decreased from 0.96 to 0.142, which the final result shows that the best performance is improve more compared to task 3 and before the adjustment of the time. Yeah, so that's the task 4.
Okay, Pastor.
Okay, next we come to the task 5 with designing the relay compensator. So we use the same similar design specification as in task 3. So the below is our cross loop plot diagrams of our relay controller. Next. Okay, so first we had to set the KV first in order to determine our steady state error. So in order to let our steady state error to approximate to 0, we set our KB equal to 250. So the steady state error will be 0.004, which is very close to 0. After that, we calculate the K by solving the limitations. We let the S equal to 0 and let the KB equal to 250. Then we get our K is 19836. Next. Okay, after that, we calculate the bandwidth. The equation of bandwidth is 4 divided by settling time and zeta square root 1 minus 2 zeta square plus square root 4 zeta power by 4 and minus 4 zeta square plus 2. Then we get our bandwidth is 44.2. Then we have to select a new phase margin frequency, which is very near to our bandwidth. So we let our new bandwidth equal to 0.8 times 44.24. Then we got 35.39. So we plot the plot. Then from the plot, we point to the frequency equal to 35.4. Then we find that the phase equal to negative 171. After that, we had to add a negative 5 correction factor. So the phase will be negative 176. So after that, we calculate the phase margin. We let 180 minus 176, then we get the phase margin equal to 4. However, the phase margin is not what we want. Since the overshoot that we want is 20%, so the phase margin that we want should be 48.2. So we let 48.2 minus 4 to get the value that the leak compensator has to contribute to in order for us to achieve the phase margin of 48.2. After getting the phase max, then we can let the phase max equal to inverse sine 1 minus theta over 1 plus theta. So we will get our beta equal to 0.1784. Next. So we can design our lag compensator first. The lag compensator is 1 decade below the new phase margin frequency, so it will be 3.539. Then the P lag will equal to beta times Z lag, so we will get 0.63. And then we got our lag compensator, which is 0.1784 times S plus 3.554 and over S plus 0.63. Then next we design our lead compensator by obtaining the Z lag. So the Z lag will be new bandwidth frequency times square root beta. So we get 14.95, and then we got our police. So the police will be 83.8.
What is your gain for lead compensator?
Gain from lead compensator.
Berapa?
One over beta. 1 over 0.1784.
Berapa?
Berapa? 5.6.
5.6. Okay.
Yeah.
Okay, conclude.
After that, then we will get the lead lag compensator next. So here we go. Then next we had to we block the open loop block for the system then we can got the gain margin frequency, phase margin, and phase margin frequency. The phase margin that we got is 51.1, which is very close to the phase margin that we want, which is 81.1. Next. After that, we brought the closed loop. From the closed loop, we can get the peak gain and the bandwidth. So the bandwidth is where the magnitude equal to negative 3 dB. Then we got the frequency is 41.1. So our original bandwidth is 44.2. So it's very close also. And the peak gain is 2.2. And for our calculations, our pin gap will be 1.8, so only 3 dB difference, which is also very close as well. So we can conclude that our system has meet the proper specifications. Next. So here we go. Here is our simulating circuit. And we can observe that the steady state error from the display block is 1.14 times 10 power negative 6. So the steady state error is very close to 0. And then we can get that our overshoot is 24%, and our settling time is 0.2663, and our peak time is 0.117867. Next. This is how we get the setting time from the output graph. So when the magnitude equals to 1.02, our setting time will be 1.266. However, this value had to be minus by 1 since the output graph of our system is started from t equal to 1x. Next. And then this is how we calculate the overshoot from the graph. The peak value is 1.24 and the final value is 1. So 1.24 minus 1/1 times 100%. Then our overshoot will be 24%. Next. Okay, so our steady state error is of our system is the output performance is 0%, is zeros, and the overshoots that we got is 24%, and the percentage error only is 20%, and the settling time and the percentage error of the settling time is 1.76%. So since all the percentage error is very small, so we can conclude that our output performance had meet the design specifications. Okay, that's all for me.
Okay.
I think we just go to the conclusion part.
No need. I already read it. Okay.
Okay.
Okay. Thank you very much, this group, Martin and the teams. Good. Okay. Thank you very much. You may exit.
All right, thank you,
Thank you,
Professor.
Doctor.
Shoshani.
Thank you, Doctor.
Jazakallahu khairan. Thank you very much. Okay, next group on video, please. Share slide, please. Miss Hugh, group Miss Hugh.
Good afternoon, Doctor.
Okay, good afternoon. Okay.
Able to see my screen now?
Okay.
All right. So I will start now. All right. Good afternoon to Prof. We are from Group 3 going to present our group assignment. So these are the group member of Group 3 and I'm Hugh Huini. So in this assignment, the system we are focused on is the position control system of the modern aircraft. And this system is used to control the position of modern aircraft fleets. So the system is represented in the block diagram as shown in figure B. And the parameters in the column C1 are used to determine and calculate the aircraft position control system. It's important to conduct the appropriate adjustment and improvement to ensure the stability, transient response, and steady state of the system meets the specifications. Next.
I think unmute your mic.
Great. Good afternoon, Doctor. And for our objectives, we have three main objectives. The first one is to design control system and implementing using MATLAB and Simulink with time, domain, and frequency domain. The second one is to design and tune a controller using Simulink model and obtain the output response. And the third one is to design a compensator using Simulink based on the given data using frequency domain technique. Now I pass it to my colleague. Next.
And good afternoon, Prof. I will be presenting task 1 and task 2 in this project. So for task 1, question A, I use the block reduction method to show the equation of the transfer function of the open loop system. And next. And this table shows the value that were assigned to our group. And I substitute all the values into the equation to get GS.
And then I created a block diagram for a unity feedback system with a gain controller, and I formed the closed loop transfer function using the formula GS over 1 plus GS. Next. And this table shows the representation of the open loop and closed loop transfer function in MATLAB. I wrote N-file and created a Simulink model for both transfer function. Next. Now let's move to task 2, which included time domain and frequency domain analysis. So we start with the time domain first. So for question A, I determine the range of stability for the system GS by obtaining the characteristic equation and using the Routh-Hurwitz table. I found that K is stable between 0 and 273.58. Next. I then found the 3 poles at 0, negative 400.26 and negative 3008.08. And then I can draw the root locus based on these 3 poles. Next. After that, by differentiate GS, HS, and psi equal to 0 to find the breakaway point. And here I obtain the breakaway point is equal to negative 193.02. And lastly, using the even polynomial from the Routh-Hurwitz table, I can find that the J omega closing points, which is plus minus 1097.28. Next. Next, I use the R locus function to draw the root locus in MATLAB. And this figure shows the poles of the root locus. Next. And this figure shows the breakaway point, K critical, and J omega closing point from the root locus. Next. From this table, you can see that the values are similar, which means my manual calculation is correct.
Louis.
Next.
Louis.
Yes.
What is the oscillation frequency when the system is critical?
Oscillation frequency?
Reverse the slide. What is the value of the oscillation frequency when the system is critical?
When the system is critical, the oscillation frequency is 1100
radian per second. Okay. Why so long?
Sorry.
Why is the answer so long? Miss you, what happened to your teammates? Nanti marah dia. Continue.
Next.
Faster. Jam.
Yeah.
Okay.
And next. And for question C in MATLAB, I use the step function to draw the output response of the closed loop transfer function and determine the system performance from the output response, including peak time, settling time, rise time, overshoot, and steady state error. And next. And in Simulink model, I created the closed loop transfer function model and use out time and out data to obtain the system performance using the step info function. And then we can click the oscilloscope to observe the output response. And next.
Louis, reverse. What is out time?
Out time is the actually
teammates help your members. What is out time? Is it out time, time out, or what?
It just a name like that.
Bila apa function? Out time saya pun tak.
Out time.
Tak tahu. Okay, nanti check. What is the value of P controller that you insert? The value of the proportional controller?
The P controller, the gain controller.
The value of P. Yalah, betul lah. What is the value of P?
Value of P.
P controller, proportional.
Not gain controller, right? It's P controller.
Same,
Oh,
same.
same. Oh, okay. 80.
80, okay. Continue. Faster.
Next. And so this is the overall view of the response, and the below one is the zoom in view of the response. So the yellow one is input response, and the blue one is output response. And we can see here that the sensor error is 0. And next. And beside that, I summarize the system performance in the table, and showing that the values from both MFOW and Simulink model are almost identical. And since K is equal to 80, is within the stable range, so the system is stable. Next, I perform the frequency domain analysis. I use the same GS and multiply it by the gain of 80 and draw the bird plot of the GS using bird function. And from bird plot, I obtain the gain margin and phase margin. Next. And from the bird plot, I obtain the gain margin and phase margin, which is 10.7 dB, and phase margin is 24.6 degree. And both margin were positive, so the system is stable. And next. And to make it become marginal stable, the bird plot must shift up 10.7 dB to make the gain margin become 0 dB. Then I calculate the gain and obtain the K is equal to 273, and this is the K critical. And I draw the bird plot with this K in MATLAB, so it is proven that the range of K is between 0 and 273. And next. And to find the statistical error, I determined that the initial slope of the bird plot, which is negative 20 dB per decade, so it's a system type 1. To find KB, I draw a line parallel with the initial slope and draw until the line cut the 0 dB line. After that, I use the formula ESS equal to 1 over KB. I found that ESS is equal to 0.001. Next. I then obtain the bird plot of the closed system to determine the maximum magnitude, peak frequency, and the bandwidth at negative 3 dB. Next. And using this data, I calculated the damping ratio and the oscillation frequency, percentage of overshoot, peak time, and setting time using the formulas. And next. And finally, I computed all the parameters for both time domain and frequency domain, and both analyses give similar results, so we can conclude that they are identical. So that's all for my parts, and I will pass to Penny to continue the presentation.
So I will be presenting task 3. So since the steady state error in task 2 obtained is 0, so only a PD controller is used to improve the system transient response as shown in figure 3.1. So the targeted design is to reduce the percentage of overshoot to 30%, and the setting time is reduced to half of its original value. So when the percentage of overshoot is equal to 30%, so the zeta and theta are as shown in the slide. So when the setting time is reduced to half of its original value, it is equal to 0.01395 seconds, and the new dominant pole is obtained as shown in the slide. So a 0 is added to the system as shown in figure 3.3. After calculating theta 1, theta 2, and theta 3, theta z is equal to 27.71 degrees. After using the trigonometry rules, the position of 0 is as negative 1710.403. And the gain of the system is obtained as shown in the slide after substituting the new dominant pole to the equation. So as a result, the compensated system using the PD controller is as shown as follows, and the KD and KP are obtained as shown in the slide. So in the Simulink, the compensated system is constructed as shown in figure 3.5.
What is out time?
I think it's the...
What is out time? Who knows? What is out time? It's not connected to the Simulink, but it's there. Is it a timer? Is it a timer? No. What is out time?
Is it to get the time response out of it?
Not sure. Who knows? Nanti check lah, update dalam slide email lah. Yeah. Okay.
So which means we need to include what is out time in the slide.
Yelah, you tak boleh jawab. Tak boleh jawab.
All right.
Okay.
So after using the step info command, we can obtain setting time and percentage of overshoot, and it will be discussed later. So from the scope, we can clearly see that by comparing the step input and the time response of the compensator system, the steady state error is equal to 0. So the method code also return to compare the parameters obtained using the Simulink, and this is a time response using the method codes. So from the table, I can conclude that the specifications are successfully achieved, where the percentage of overshoot is reduced from 49.5% to 30%, and the setting time is reduced to half. And this system achieved the steady state in a shorter time, and it is more stable. So next, I will pass the presentation to colleague Ham.
Thank you, Winnie, for presenting the task 3 findings. Now
Faster.
Now I would like to present the task 4, which is the tuning of the PID parameters. In this task 4, we are using the automated tuning method, which the PID tuner approach is used by selecting the tune in the PD controller block to obtain the correct tune response. The percentage overshoot is set as 30%, and however, the setting time may be different due to the tune gains KP and KD. So next, for the case 1, when slider is moved slightly to the right, which is fastest response time, and slider for transient behavior is moved to the left, which represents the more aggressive transient behavior. The tune response shows the setting time of 2.74 milliseconds, where the steady state error is 0 and percentage overshoot is 30%. For the case 2, when the slider is moved to the right and the slider for the transient behavior is also moved to the right, the tune response is tuned at the 30% overshoot with a setting time of 1.66 milliseconds and 0 steady state error. For the case 3, when the slider is moved even to the right and even to the left for the transient behavior slider, the tune response is maintained at 30% overshoot as case 1 and 2, where the setting time is 2.4 milliseconds. So based on 3 cases, the results are tabulated in table 4.1 and table 4.2. So next. Based on the table 4.1, the case 3 specification, which the KB equal to 353.9368 and KD equal to 1.2528 is the best specification since the setting time is smaller than original response. For the frequency domain analysis shown in the next slide, the system is stable, where the next slide. For the table 4.2, by using the frequency domain analysis, as shown in the PID tuner parameters, the case 3 is the stable system where the gain margin is 26.7 decibel and phase margin is 38.1 degree, which are positive implies that the case 3 system is stable. So now I will pass to the Noah for presenting the task 5. Thank you.
So here we have task 5, and which is to design a lead lag compensation. Here we have lead compensators design, which is used to improve the transient response, like overshot, percentage overshot, and settling time. We can see here in the figure the closed loop block diagram of the lead compensator. Next. Here we have select the specification from task 3 as requested, which is we got 30% overshot for the targeted phase margin, which is 39.10. And since our steady state error is 0, we will not do the lag compensator, which is not compulsory. We'll only do the lead compensator. So we have to use the formula to obtain the the zeta. We got the zeta here, 0.358. Also for the phase margin out from the zeta, we got 39.10. Next. So here we have the system before compensation. We can see here the code we used in MATLAB. And here it's the open loop bot plot before compensation. We get the gain margin frequency, 1100 radian per second, gain margin 10.7, phase margin frequency 566, and phase margin 24.6. Next. Here we also see the closed loop bot plot before compensation. We plotted the code and the transfer function to get the phase margin. We got 22.377 and frequency 589. When the magnitude is equal to -3, the bandwidth frequency will be 917. Next. So here we can see after compensation, the system, our targeting phase margin will be 39.10, while the measured phase margin is 24.6. So we are using correction factor, which is equals to 10. And the maximum, since we calculate the maximum phase margin, we got 24.5. Here we want to obtain the beta. We got the beta, which is equal to 0.4137. Also, we calculate the compensated phase margin to get, the magnitude. We calculated the compensated magnitude, and we got -3.835. Next. So here, after compensation, when the magnitude is equal to -3.835, the maximum frequency will be 326. So we want to get the ZC. So we use the formula to obtain it, which is we got 466.96. Also, we wanted to calculate the PC for the lead compensator. We also got 1128.74. Next. So after compensation, the lead compensator is, as the equation shows below, we got the transfer function. So the overall system, we obtained it.
What is the value of the gain of the lead compensator?
Of the lead compensator?
The gain.
The gain. -3.835.
Negative?
3.835.
3.835. Astaghfirullah.
Oh, the gain. We used...
gain value of the lead compensator.
I think we used the same value, which is 80.
Astaghfirullah. It's wrong. It's written there in the red color. What is the gain value of the lead compensator? You wrote in the right red color.
Oh, 2.417, yes.
Okay. Conclude.
Next. So here we have the open loop bot plot after compensation. We get the gain margin frequency, 1770, the gain margin, 12.9, and the frequency of phase margin, and the phase margin. Next.
Allah.
Here we have the details for the closed loop bot plot after compensation also. We got the MP equals 1.479. The frequency.
What is the explanation for feedback? Bracket G, 1. 1 stands for what?
Feedback.
Back bracket G, 1. 1 stands for what? Members, please help.
1 stand for unity feedback. K equal to.
Okay, unity feedback. All right.
Okay. So here, when we got when the magnitude equals -3 dB, the bandwidth frequency will be 1260. And now I can pass it to my colleague.
Okay,
So, we continue the Simulink part of the system. So this is a system constructed before the compensation in the Simulink. And using the step info command, we can obtain percentage of overshoot, setting time, and peak time. And this will be compared later. So same as the compensated system, this is the system constructed in the Simulink. And the step info command also used to obtain the 3 parameters. So both the before and after compensation system are connected to the same scope in order to observe the steady state error after and before the compensation. So from the figure 1.6, it can be clearly see that the steady state error is equal to 0 before and after the compensation. So from this table, I can conclude that the specifications are also successfully achieved, where the percentage of overshoot is reduced from 49.5% to approximately 30%, and the setting time is reduced to half, and the peak time also reduced from 0.059 seconds to 0.036 seconds. And this system is reached the steady state in a shorter time, and it is more stable.
Thank you, Rini, for presenting the task 5. Now I will presenting the task 6, which is the comparative finding analysis from task 2 to 5. So these results are based on 3 aspects, which are output response, efficiency, and stability. For the output response, the task 2 has achieved the greatest setting time and peak time, which are 27.9 milliseconds and 5.964 milliseconds respectively, whereas task 4 have achieved the lowest setting time and peak time, which are 0.773 millisecond and 2.4 millisecond. However, due to the task 4 higher filter order of the design, the cost implementation is higher, so the task 4 design is not so the best design. So task 5 is the best design, where the setting time and peak time is the lowest, which are 3.6 millisecond and 12.2 millisecond. For the efficiency response, as the next slide, it depends on the percentage overshoot factor.
Okay.
It means that, I'm sorry.
Yeah, okay. Understood. Conclude, because time's up. Okay.
So as for the conclusion, we have designed the aircraft altitude system, and we achieved the objectives that we set at the beginning. We got the overshoot correction. We got also the steady TS settling time, half of its origin. And thank you for listening. That's all.
Okay, thank you very much, Shashini. Jazakallahu khairan.
Okay, thank you, Prof.
We exit and
Prof.
other group.
Thank you, Prof.
Thank you.
Next group, group number 15.
Yeah, doctor.
Sure. Oh,
Yes, doctor.
ah,
Good afternoon, doctor.
okay. Share slide, please.
Doctor. Okay. 看到我 share。
Slide. English, please. No Chinese, no Mandarin. English, please.
Okay, doctor. Can you guys see my slide?
Yes. Yes.
Can. Okay, now I will start the presentation. Good morning, doctor and my friends. We are from group 15. We are from group 15, and my name is Yofui. And my as a group leader, my sorry, sorry, doctor, I continue. I'm group leader Yofui, and my teammate is Tong Kim He, Im Wei Lian, and Yak Chen Jun. And our assignment is to do the control system on the position of the fin of a modern aircraft. And this is our group system parameters. And now we will start our task. For the task 1A, first of all, we will do the block reduction method to get the transfer function of the open loop transfer function. And the first step, we will move the takeoff point from the IA to the omega m. Then we will form 3 feedback structure of the block diagram. Then we will do the simplification. And finally, we will get our open loop transfer function. And now we go to task 1B. In the task 1B, we plug in the value system parameter from our group, and we will get this open loop transfer function with post 0, negative 558.666, and negative 1716.332. In task 1C, we will obtain the closed loop transfer function by putting the gain k equal to 120 and a unity feedback. And this is our closed loop transfer function. In the task 1D, we will use the MATLAB to show our open loop and closed loop transfer function by using the coding. And also, we will get the poles and zeros in the MATLAB. Now we'll go to task 2. In the task 2, we got two parts, which is time domain analysis and frequency domain analysis. In this task 2.1a, we will do the manual calculation to sketch the root locus, and this is our root locus, and we will gain the range of stability gain, which is from 0 to 242.38. And this is the calculation for finding the breakaway point and also the J omega closing. And we found that our breakaway point is negative 252.91. The J omega crossing is plus minus 979.22.
Stop.
Next,
What is the oscillation frequency during critical stable? What is the value of the oscillation frequency during the marginal stable?
The marginal stable, the K critical is 242.38.
The frequency oscillation. The oscillation frequency. Reverse lah, reverse. First time. There. What is the oscillation frequency when the system is marginal or critical stable?
I think maybe in frequency domain analysis.
Members, please help.
I think is 979.22.
Okay, radian per second. Okay, check it out.
Okay.
Continue.
Okay. Now we will go to task 2.1b, and in this question we will plot the root locus by using the MATLAB, and this is our root locus. From the root locus, we obtain the gain, which is 240 until 242, and the J omega crossing is plus minus 979, and the breakaway point is negative 253, which is similar to our manual calculation. So
What is the closed loop value when the damping ratio is equal to 1? What is what is the closed loop pulse value when the damping ratio is equal to 1? Itulah tadi tu. Tadi tu. Bukan. Reverse. Forward. Tadi gambar tu mana? Gambar tadi tu. Ni. Bila damping ratio equal to 1, berapa? Close loop pulse ni.
Damping ratio equal to 1.
Ni dekat breakaway point ni. Apa dia punya close loop pulse dia?
Wait.
No need. Jangan.
Okay.
What is the closed loop pulse value at the breakaway point?
Negative 253.
Betul. Mana itu 253. Ayah, tukar nama je mah. Tukar nama je. Breakaway point tu closed loop pulse lah. Tukar nama je.
Okay.
Exam buat exam jaga-jaga sikit.
Okay. Can I continue?
Continue.
Now we will move to 2.1c. In the 2.1c, we will find the time response by using the mainlet and Simulink. And first we use the mainlet coding, and this is the step function, and step info we use to get the system performance of the closed loop transfer function. And this is the this is the code, the system response of our system. We'll found that the overshoot is 59.1, and the peak time is the 0.0045 second, and the setting time is 0.0364 second, and the final value is equal to 1. So we can conclude that there's no steady state error for the step input. And next, we will use the Simulink model to do again the system performance analysis, and we found that the rise time is, we found that the the setting time is 0.0321 second, and the overshoot is 55.5 second, 5%, and the peak time is 0.005, and the steady state error is 0.
Oh,
And
reverse. Tadi Simulink. What is the value of the proportional controller that you used?
120.
120. Toi. So what is the function of out in the Simulink? AUTT, out. Ada jam tu. OUTT tu.
One is to get the value, the magnitude of the y-axis magnitude, and the other is to get the time.
Time. That's why the clock.
Clock.
Okay.
So we can plot the graph.
Okay. Time tu lah. Okay.
This is the graph of our system using the Simulink. You can see that it is similar to the graph of the using mainlet coding.
Okay. Faster.
Okay, now we will go to the frequency domain analysis. We will use the subplot, bot, and the margin function to find the phase margin, gain margin, and their frequency. This is the open loop bot plot in our left hand side. The gain margin is 6.11 at frequency 979, and the phase margin is 18.4 at the 761 frequency. And for the right hand side is the closed loop bot plot. We found that the -3 dB magnitude, then we can get the bandwidth frequency of the system, which is 1.07 times 10 power of 3.
Stop. What is the value of the gain crossover frequency?
Gain crossover frequency is 979.
Itu phase crossover frequency, gain crossover frequency.
679. 671.
671 radian per second. What is the phase crossover frequency?
979 radian per second.
Okay, continue.
Okay, then we will find the stability gain of the system, which is by using the gain margin. Then we get 2.021, and we will use the final value theorem to find the steady state error. For the unit step, the steady state error is 0, and for the ramp function, we found that the steady state error is 8.878 times 10 to the power of -4.
Zero lah tu. Zero lah.
Similar to 0. Then we will go to task 2.2b to find the maximum magnitude, bandwidth, and the percentage overshoot, damping ratio, peak time, and setting time. From the closed loop bot plot, we can find the peak gain equal to 10.3 dB. Then we will get the maximum magnitude. Then you can continue use the formula to find the damping ratio and also the overshoot percentage. And then we'll use these two formula to find the setting time and peak time. And the final value for the system output performance is at this side. And we will go to the task 2.2c, which is compare our result in time domain and frequency domain. Basically, we have three methods to find the same system parameter, and these three parameters are almost similar with very little difference between these three methods. So we can make a conclusion. Both the time domain and frequency domain technique they be used already confirm the system stability and acceptable performance.
Okay, faster.
Okay, that's all for task 1 and task 2.
Next, I will continue for my task, which is task 3. In this task, we are going to design obtain the better improvement based on the output response in task 2. Hence, the PID design is used in this task. In figure task 3A, we can see that our new TS value is 0.0121, which is 1/3 of the old setting time. And the new OS overshoot value will be 29.57, which is half of the old overshoot setting time. And the steady state error will remain 0. In task 3B, we can see that there's a block diagram of the PID controller block that would be executed in the simulation. Next. Hence, in this task 3C, we are going to obtain the KP, KI, and KD parameter of the PID controller, which will be used in the simulation to decide the spec of the PID. And to obtain the new dominant pole, we are going to obtain the new zeta first, which is 0.3616. After that, we will be using the formula of TS to obtain the dominant pole. To obtain the dominant pole of the, hence we can find that negative the real part of the dominant pole and also the imaginary part of the new dominant pole. Hence, the new dominant pole will be negative 330.5x plus jx 52.35. Next. Hence, to design the GPID, firstly, we have to design the GPD first. Firstly, we need to get the location of the zeros. Hence, we can from the calculation we can observe that the delta of the zeros is 71.x7, which is less than 0. Hence, we can say that it will be located in the left hand side from the new dominant pole. Hence, the zeros will be in the negative 609.66. Next. Hence, this is how it looks like. Next. Hence, next we need to obtain the KD by substituting the new dominant pole. Hence, we will obtain the 0.1626. After obtaining the GPD, we need to multiply with the GPI to obtain the GPID. For the GPI, it will be S plus 0.5 divided by S. After that, after multiplication, we need to compare with the formula to obtain the KP and KI, which are 99.21 and 49.57 respectively. Next. As this output response after added the PID controller. And next, by using the step info function, we can obtain the TS and overshoot. For the TS, it will be 0.0130, which is close to the desired expectation. And for the overshoot, it will be 31.1205, which is also close to the expected design value. And for the peak time, it's exactly same with our design. For the ESS, will be 0 also. Next. Hence, we can say that the output in fact, the output performance does not meet the requirement of the design specification, which is due to the existence of the steady state error, which is 7.44% of the TS and 5.24% of the overshoot. And for the TP and ESS remain the 0. This is due to the coefficient, filter coefficient n in the spec of the PID rod. We found that as n getting higher, the result obtained is getting close to our expectation, but it doesn't meet exactly as we wanted. So we only can obtain the nearest value. Next, I will pass to my neighbor to continue.
Okay, thank you,
Thank you.
sir.
Faster.
Okay, now I will explain on task 3. Actually, in simulating, the PID controller can be used to find the PID gains to achieve the optimal performance of the system. Next. Okay, this is because the PID controller in simulating is equipped with an optimization algorithm which can perform better and faster in obtaining the optimum gains for the desired system. Therefore, we do not need to perform the tedious calculation like in the Ziegler-Nichols method or what we show in the method in task 3. Next. All this. For example, by adjusting the slider values under response type and transient behavior, we can quickly obtain the PID gains to achieve the best spec of the system. Next. Okay, we get the best spec of the system, which is 1.25 overshot and 0.0117 seconds settling time after adjusting the slider. Then we simulate the simulating modules with these new PID parameters and then get the same result. Okay, now William, you explain on the task 5. Thank you.
Okay, in task 5, we are going to design a lead compensator to achieve our desired design specification. Our design specification is shown in the figure task 5A. And part B is the closed loop block diagram in Simulink. Next. And in this task, we are going to design and find the Z value, zero value, post value for the lead compensator. And we set our correction factor to 10 degrees, and the original bot plot is the phase margin is 18.4 degrees, and the required phase margin provided by the compensator is we put inside the formula to find it. And then from the required phase margin, we can find the beta value and the K extra, and we use the K extra and in gain adjustment technique to find our omega max. And then from our omega max, we can find our zeros post for the lead compensator. And then based on our lead compensator, we multiply with the original function and we feedback with unity to get our closed loop buffer. And then we use stack info to find the transient response of the function. Next. And then this plot diagram is the original bot plot open loop, and the right hand side is the result of beta, Z, P, and the lead compensator functions. Next. And then for the case correction factor equals to 10 degrees, it can be seen that the phase margin is 34.4. Actually, our design specification is 39.5, quite near, but actually there's a 10% of percentage error. And we can see that the transient response is improved because the bandwidth is 1500 and before is 1070. Next. And then we adjust our correction factor to become 21.2, and we find that the corresponding omega max is equal to 1034. And then we can see from the open loop plot, the phase margin is achieved 39.5, and the bandwidth also increased. But the next, okay, and then from this Simulink diagram, we can see our transient response result. And the settling time is 0.0086, actually is less than our desired specification, which is 0.0121. And the steady state error from this Simulink is 0. And we also achieve our overshoot, which is 29.32, similar to our desired 29.57. Next. Okay. This table is to compare the output performance in between two correction factor. For correction factor equal to 10 degrees, actually the percentage error of overshoot is quite high, but the settling time almost the same, and there's no steady state error. And for correction factor equal to 21.2, we achieve our overshoot, but the setting time become lesser, and the steady state error continue as zeros. And we can conclude that the correction factor are crucial in designing our design specification. Next.
Okay, thank you, William. Okay, next. Next slide. Next. Okay. The system in task 2 has different stability compared to others. This is because the implementation of PID controller and lead compensator has caused changes in gain margin. The change in stability is depend on the gain or zero pulse of the compensator system. Next. As shown in the table, by using the tuning tools of the PID controller in simulating, we can let the system to achieve the best performance in response characteristic in task 4. Next. If we look into the result in task 5, it can be observed that the different correction factors in the lead compensator can affect the performance in both stability and response characteristics. Therefore, we can conclude that the correction factor should be adjusted according to the desired system spec. Thank you. Okay, thank you, Doctor. This is all for our presentation. Thank you.
Okay, thank you very much. The utmg15.com. Is this what? What is this?
Only a name.
Fake line, huh? Okay, all right. Okay, thank you very much, Shashini.
Thank you, Doctor.
Yeah, doctor.
Thank you, Doctor.
Good, Prof.
Okay, G7, last group. Your group may exit. Okay. G7 on video. Yap Sun Yu, Solihin Sukri. On video, Teh Ya Chian, Tio. Oh, mistake. Miss Tang best friend. Tio on video. Okay, can share screen and start. Oh, Mr. Jin. All right. Okay, start.
Okay. Assalamualaikum and a very good evening, Dr. FUA'AD. So we are from Group 7. We are going to present our assignment. So here is our team member. First is Tayah Chian, Teo Chi Jin, Yap Sun Yu, and me last, Ahmad Salim bin Sukri. Next. So as introduction, attraction, we need to do modification or improvement on attraction drive motor system so that the purpose is to avoid the disturbance. Next. Here is the diagram of the traction drive motor system and the capstan roller, and this is the block diagram. It's given in the questions. And the table below is the parameter given for the traction drive system. Next. Okay, here on the screen we can see the objective. The first objective is for first task, determine open loop and closed loop transfer function. The second objective is for task 2, analyze in time and frequency domain. And the third objective is for the task 3 and 4, PID controller and PID tuning of PID controller. And objective 4 is for the lead compensator, improving the parameter of system. Next. So here is the modeling. The generalized transfer function GS as given in the question. So we just need to substitute all the parameter given into the equation. So here is the open loop and closed loop transfer function generated by the MATLAB. Next. Okay, here is the MATLAB coding and result for the open loop transfer function. We simply use all the parameter, declare all the parameter given and use the command G equal to X over V to get the transfer function, open loop transfer function. Next. Here is the MATLAB coding for the closed loop transfer function. The same as the one before, we just add the closed loop transfer function annotated as T equal to feedback G1. This determine the annotate that the system is using the unity feedback system. Next. So we continue with task 2.
Hi, Prof. I'm Chi from Group 7, representing task 2. So in task 2, we are separating into time domain analysis and frequency domain analysis. First, let's talk about time domain analysis. In time domain analysis, we are mainly dealing with root locus. In root locus, we have to find several informations such as the maximum K, JW crossing, BAP or BIP point. So first of all, let's talk about the stability gain. So we are using RH table. By using RH table, we can find the maximum K value is equals to 36,300. So this 36,300 is representing the maximum value of K for the system to be stable. Upon this value, the system will start becoming unstable. Next, let's look at the JW crossing. So substituting the value from the K into the equation, we'll obtain plus minus J equals to plus minus J 95.69. This value is representing the JW crossing, so-called the y-axis crossing. And also we have to find BAP or BIP points, and differentiating these equations, we'll get negative 7.6 and negative 397. So we are going to choose between these two values and see which value is the most fitable or suitable one. So let's sketch the root locus. From the root locus, there are three branches altogether. So from the first two branches, negative 7.6 is the most suitable value to be the BAP, breakaway point, as the direction is away from the x-axis and crosses at negative plus minus J94.69 as the JW crossing.
Stop. Reverse. Reverse. Mr. Jin.
Yes.
Reverse, please. May I know? Reverse, please. No, the root locus. Yes. Okay. May I know what is the oscillation frequency when the system is marginal stable?
94.689 radian per second.
And then may I know what is the closed loop pulse value at the breakaway point? What is the closed loop pulse value at the breakaway point? Jangan, don't change. Don't change.
Negative 7.6.
Huh? Again?
Negative 7.6.
Toy. Okay, continue faster.
Okay, now let's look at this one is the code for the time domain analysis. We are using R locus G to sketch the root locus using MATLAB. And the above is the step response. And in this step response, there are several information such as setting time, OS, rise time, peak time, and also the final value. So from here, we'll notice that the ESS is equals to 0 because the final value is 1. Next, we proceed with the Simulink. This is the block diagram, closed loop block diagram for Simulink function. From here, this is the output graph waveform generated in the Simulink itself. And from here, we notice that the shape for both time domain analysis in MATLAB script and Simulink are similar, and the values in terms of time response are also similar.
Stop. What is the out? Sim out stands for what?
Sim out means that we are actually output the value to the command terminal.
Command terminal. Yes. What is the proportional controller value that you used?
It's 4,000.
4,000. Okay. Sorry.
Next, we proceed with frequency domain analysis. In frequency domain analysis, I'm actually using two commands, which are margin and dot commands. Why the reason that I implement using these two commands is because if let's say I'm using margin G, this is for OLTS, for margin, there are actually the system, the MATLAB will show the value of GM and PM directly onto at the title of below the title of our plot instead of finding the values manually.
Stop. What is the phase crossover frequency value? Phase crossover frequency value.
Negative. Sorry, for phase
crossover frequency value.
WPM is equals to 30.4 radian per second.
Oh, that is gain crossover frequency value. Phase crossover frequency value.
95.7 radian per second.
95.2 radian per second.
0.7 as shown in the title.
Oh. But in the computer 95.2.
This one is we use the cursor to show the value, but the actual value is 95.7.
Oh, okay.
95.7 is the most accurate value using the margin command.
All right. Okay.
Next, this one is the calculation to find the value of stability and also ESS. So by using the final value theorem, ESS is nearly equals to 0. This is the dot plot of closed loop transfer function. From the closed loop transfer function, we can get the maximum peak with its respective frequency and also the bandwidth by finding the W at negative 3 dB. So the bandwidth is 48.3 radian per second. And the peak is 7.62 dB. So by substituting the values obtained from the closed loop into the equations, we will get the value of MP and also zeta respectively. So for the zeta, there are actually two values, 0.2128 and 0.9. So from these two values, we are choosing the value which will produce the percentage OS similar to the one in time domain analysis, which is around 50%. So zeta equals to 0.2128 is adopted because the value provided will be 50%. Next, we also make use of the zeta value to calculate the value of TS and TN. And both of these results are displayed in this table. And from here, we will observe that the value between time domain and frequency domain analysis are similar. So this is the conclusion for task 2. Next, we proceed to task 3.
I'm Mia Chen. I'll explain about the task 3. In task 3, we design the system with PID controller. The spec that we set are reduce the percentage overshoot to 30%, setting time to 0.4 seconds, and remain the steady state error equal to 0. Figure 3.1 show the PID controller board that we want to design after this. Next. Before this, we need to find out the value of the KP, KI, KD by calculation. First, from the graph of the percentage overshoot per theta, we can find the theta value and use the setting time that we set to find the Newtonian pose. Second, we use a trigonometry method to find the Z1 value for the PT controller. And next, we set the Z2 value for PI controller equal to 0.01, and thus we can find the K value which is equal to 22.04. And last, from the equations of the GPIT, we can find the KP, KI, KD value, which KP equal to 2955.12, KI equal to 29.55, and KD equal to 22.04. Next. This is the Miller code that use the calculated KP, KI, and KD value to plot the state response and root curves after the PID controller. For the state response graph, we use a crossroad system. We use a crossroad equations. While for the root curves graph, we use the open root equation.
Stop.
Okay.
Ya, mesti ni baca macam pembaca berita lah. Apa maksud feedback bracket GPID, 1?
This one is to calculate the crossroad equations.
So 1 stands for?
1 stands for the unity feedback.
Unity feedback. Betul?
Yeah.
Continue.
Okay, next slide. This two graph is the Lulocus graph, and from the Lulocus graph, before the PID controller and after the PID controller, we can conclude that after the PID controller, the Lulocus graph is more stable than the before the PID controller. And next. These two graph is a set response graph, and we just use the viral mouse and right click, and we can show the overshoot, a percentage overshoot, settling time, and also can show the steady state error. From the graph, we can show that after the PID controller, the overshoot is 30.4%, and the settling time is equal to 0.387, and the final value is equal to 1, and mean that the steady state error is equal to 0. Next slide. Besides using the stat response graph, we also can use the stat response informations. From the stat response information in the MATLAB code, we can show that the settling time, overshoot, and also the peak time. Next. This is the output response by the Simulink. Figure 3.9 show the PID controller blocked by using the Simulink model. And the figure 3.10 is we just using the two cursor, and we can show we can determine the setting times by using the two cursors. And next. This one is the graph to determine the overshoot, percentage overshoot. Also using the two cursors, we also can determine it. The next slide. Table 3.1 is a comparison between the design specifications and the MATLAB and also Simulink result. First, from the table 3.1, we can conclude that the design spec by using the PID controller are achieved. Next.
Stop. Mr. Why the value is different between MATLAB and Simulink?
I think the value is different because by almost the same, right? By using the MATLAB is 0.387. We also can
Can you comment why it's not the same?
Simulink is 0.437, maybe
because the plot diagram there for the transfer function in the MATLAB, it can detect more decimal places. For the transfer function in this, we are using when using Simulink, we put less decimal places, and that's why there's a small difference there.
Is there's precision issue. Oh, Mr. You punya team member very good lah.
okay. Yeah.
Good backup. Continue.
Okay, so now I'll continue for task 4. Task 4 basically is just about the PID tuning. It's using, okay, next slide. Next slide. Okay. 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 Next slide, please. Okay, this one. Also, so the PID tuning for this task is just improving the TS and the percentage overshoot to test if we can improve more. The bot plot diagram. This one also can. This one can we just continue from here? So the PID design specs, we just using KPKIKD from task 3, which is from Yachen's task. And then we continue next slide. Next slide for the parameter for the transfer function.
Is the slide moving? Is the slide moving?
Okay, now is it moving? Okay, so this one is for the transfer function we got from task 1.
Is the slide moving?
Yeah, moving already. So this one is the parameter we got from task 1. And then we continue. Next slide. Oh, suddenly Chijin Jam. Never mind, doctor. I'll just explain more a bit. So this one. Okay, so this one is go back to the graph. There's the overshoot graph under then response. This one. So this one is just also another showing to prove that my result is I'm using the same result from past trade. Okay, so continue next slide. Okay, so here this slide is the main objective of this task, because it's about the PID tuning in a PID tuner app inside the Simulink of the PID model. So when you run a PID tuner app, you get a GUI like this. So there is a tune response and a block response there. And next slide. And then we'll select the response type and transient behavior above there, above part. So we'll select until when, okay, next slide. Okay, we select until the response become very sharp, and then you can see that for the tune response, the performance and robustness, the TS become very small, 0.165 seconds. And the percentage overshoot also reduce very much. So when do we stop? We stop until the TS, and then if we slide more, the TS will become n second in the parameter now. So we just stop here. This one is the least value that I could provide. Next slide. So after I get the new response, I update the block in the PID tuner app, and I'll get new values for KP, KI, and KD. Next slide. So now I want to test the new ESS. If the ESS is still 0 when comparing the PID signal with the input signal, you can see that I input one more input signal to the scope. Next slide. Okay, so the input signal, the blue one, and the yellow color is the PID signal. So after they become stable and then they overlap with each other, so means that the ESS is equals to 0. And that's all from me for task 4.
Continue.
Next, back to me again. In task 5, we are implementing a compensator between leak and lag compensator. Since in task 2, the ESS is nearly equals to 0, so there is no necessary to implement lag compensator due to the cost. So we just implement leak compensator. In the design of leak compensator, this is the design specification brought from task 3, which is percentage overshoot with cap at 30%, TS at 0.4, ESS equals to 0, nearly equals to 0, with the KV value of 605. This is the closed loop block diagram of leak compensator control diagram. So first we have to find the value of K, and the K value is equals to 36,000. So since the ESS value is small, so as again, leak compensator is used instead of lag compensator. So after forming the equation of G nu in the form of transfer function, we can substitute this transfer function to the MATLAB. And this is the board diagram of the MATLAB using the G nu function. So next, using the correction factor of 10 degree, so our max phase PM is equals to 49 degree. And by using this 49 degree, we are going to calculate the value of beta for leak compensator. So after substituting the values, we will get beta is equals to 0.1395. And we will notice that the value, yes, we will notice that the value of beta is equals to 0.1395, which is smaller than 1. And this is true for leak compensator. Next, we proceed to find the value of J omega max. And by using this value, 2.67, to get the value of ZC and PC. So substituting the value of 2.67 and in the board plot, we will get the dB in 8.55. And from here, we reflect the image of 8.55 to the negative x-axis. We will obtain the value at the frequency of 155. And this frequency is the W max, maximum frequency. And for this, we can obtain the value of ZC and PC, which are to be 57.8 and 414 respectively. So we can substitute the value of ZC and PC into the general equation of GC in the form of transfer function. And this is
Stop.
the, yes,
What is the gain value for your lead compensator?
7.16.
Okay, sorry.
And now the ultimate G lead in the form of transfer function is to multiply the value of G new together with the GC. And in the end, the gain value is 6.8 thousand for the K value. And we substitute this value into the MATLAB to obtain the bot plot. And this is the bot plot. And from here, using the command margin, we'll notice that the phase margin is kept at, the frequency is at 155, which is proven to be true for the value 155 we adopted in the calculation. So the value
Targeted 49, achieve 40. Targeted 49, achieve 40.
Yeah.
Okay. Okay.
There's a 10 degree of difference.
Okay. Continue.
So after we also plot the closed loop block diagram at the same time as shown in figure 5.6. This process is to get back to check back the value of percentage overshoot. They are the value obtained in the closed loop block diagram, such as the value of P and also the bandwidth. So from the value of P, which is 3.35 dB, we'll get the value of MP, and from MP we can substitute back into the equation and get the value of zeta. So again, this zeta value come with four roots, with two positive roots and two negative roots. From the two positive roots, there are also two answers, and we are going to choose the solution which will give us 30% of overshoot, which is zeta equals to 0.365. Also, we can use the phase margin curve to check back our calculation. So for the percentage overshoot of 30 degree, the zeta is equals to 0.36, and we bring forward the 0.36 into the graph of phase margin against damping ratio, which is zeta, and we'll get back the degree is 40 degree. So when we check back the 40 degree in the block plot, the value are similar.
All right, good.
Next, we proceed to the task in Simulink. This is the block diagram, closed loop block transfer function in Simulink. This is the output waveform after running the block diagram. And from here, we'll notice that the ESS is equals to 0, although no lag compensator is adopted. So proving that there's really no necessary to implement the lag compensator. And from here, the response, transfer response has been improved. So this is the table comparison between MATLAB and MATLAB script and also Simulink. So we'll notice that the values slightly deviates, especially for the flattening time. For the peak time, they are equivalent 0.018 seconds, but for the flattening time, that slightly deviates by 0.03 seconds between these two. One of the reasons could be the precision issue mentioned by Yap just now. And also for the percentage overshoot, we achieve 36%. However, in the design specification, we have set it to be 30%. But this 36% should be good enough because we have drastically reduced the percentage overshoot from the original value, which is 50 to 36, which has been reduced by 48%. So we will consider the result achieved in task 5 using the compensator technique.
So now we move on to task 6, the comparative analysis. So we can tell by looking that all the tasks have successfully achieved their requirements. As we can see, the task 2 have the highest settling time, peak time, steady state error, and overshoot percentage, and gradually decrease by continuing to task 3, 4, and 5. Now we take a look at the most important, the task 4 and task 5. The task 4 is for the tuning of PID controller. The task 4, we get the steady state error 0, which is very stable, and very low overshoot percentage. While not to forget about the leak capacitor, even though we have a high overshoot percentage, but the leak capacitor is good for achieving faster settling time and peak time. So we can move on to finding. To finding, both PID controller and lead capacitor are effective in improving the system percent overshoot and settling time. So for PID controller, it is versatile and widely applicable, provide balance improvement in stability. On the other hand, lead compensator excels in fine-tuning specific performance characteristic. Offers targeted adjustment for precise performance enhancements. So to conclude, both PID controller is prepared for broad stability and response improvement, while lead compensator is more suitable for precise control over some specific parameter. And that's all from us. Thank you.
Where is your list of reference?
Doctor, may I take my leave now? I got classes.
Okay, okay. Thank you very much, session ni, Miss Tay and teams. All right. Thank you. See you later.
Okay, thank you.
Thank you, Doctor.